Hey, so I would like to talk about the mass and spring system, combined system that we were looking at earlier this week. So let's say that we have right here, let's say that we have a wall, okay? And let's say that here we have the pavement. Okay. Now, let's say that we have a spring here. So this is a spring that has a spring coefficient of K1, and that is tied to a mass right here. And it has wheels, so it's frictionless. And let's say that we have another one connected to this first mass. So I'll call this M1. And we have another mass here. Let me make the floor longer, like that. And this also has wheels, so that it's frictionless. This is M2, and this is our K2. And let's say we have another spring right here, and this is spring M3. Like this. So we have these three masses. Now let's imagine that this is the equilibrium x, positive this way. Same for this one, x, say this is x1, this is x2, positive this way, and the last one right here is x3, positive this way. Now, I'm going to pretend that there's a force here that's pulling this whole system this way. How would I model the position with respect to time of each mass? So let's focus on the first mass. So for M1, if that was by itself, it would have two forces, right? So if I were to look at this stuff right here and look only at the horizontal forces, I would have this cube, and then I would have, well, if I am pulling, then K2 is going to bring a force, that second spring is going to bring a force this way. And this force is going to try to bring it back, F1. So, how would I write this? Well, I would say that the mass 1 times the second derivative of position with respect to time is equal to the first force is going to be negative K1, is coming from the first spring, times x1, right? The more you displace it this way, the more this is going to want to pull back. And the other one is going to push it forward, push it in the positive x direction, by an amount equal to the difference of this, right? Assuming that this gets moved here, this gets moved a little bit, the difference is going to be how much it is moved by, it is pulled by K2. You just have to think of this. Think of this moving a little bit here, and think of this moving, let's say, a little bit less. Then we find a difference, and the difference is going to be how much K2 is going to be stretched. Now, I'm not fully understanding this. So this is, if this is equilibrium and this gets moved by this much, and this gets moved by this much, all we have to do is we have to find a difference between this distance and this distance. And right now we just have k2 minus x2 minus x1. But I think it's because there's a net effect. So if I put k2, that's going to be x2 minus x1, and that's going to be our first mass. Then I can copy this. So let's copy it, and I'll paste it down below. So we have it here, and I'll paste it down below again so that we have it over here. Okay, so now we're going to say that this is M2 and this is M3. M3, M2. We're going to say that this is this right here. So let me make this orange. And this is going to be F2 and F3. This was M1. This is M2. So here we're going to have M2 times acceleration, that's Newton, is equal to the sum of the forces. Well, what forces do we have? Well, we have this force over here, but now it's pulling back because the force that the spring exerts is the same on both sides. So that's going to be negative k2 times x2 minus x1. And then we're going to have the F3. And this spring is going to try to pull it to the right. This is K3, because we're imagining that we're pulling this whole system. So that's going to be positive K3 times x3 minus x2. And then we can look at this last one. We'll say that this is for this guy right here. And this guy, this is M3, is going to have only one force, which is the force of the spring pulling back right here. Why? Because we're assuming that this force right here is kind of like an initial condition, but then you leave it by itself. Like you don't have anything. You leave the system by itself. So the only force is going to be pulling back, so in the negative direction, and it's going to be x3 minus x2. Now, what we can do to solve it is we want to make this a system of first-order differential equations. So we know how to do that for a single one of these.